This video covers motional EMF and induced currents. So let's say that you have a metal conducting rod with neutral charge and it is moving at a constant velocity through a uniform magnetic field. If you use the right-hand rule that we talked about in the previous video, then there is an upward force on the protons due to the magnetic field. And then there's a downward force on the electrons due to the magnetic field. So these forces are actually going to separate these two protons and electrons. So a force of magnetism is going to separate them, but we know that positives and negatives are attracted to each other, so the force of electricity is going to attract them or try to pull them together. But if these charges are not accelerating anywhere, then the forces must be equal and opposite. If the forces are equal and opposite, then we can set the electric force equal to the magnetic force, namely QE equals QVB. Again, the Q's cancel, we've seen this equation before, and we get the electric field is equal to the velocity times the magnetic field. But one of the other things we want to notice here is that there is now a potential difference between the ends of the rod. Again, remember that we talked about a positive and a negative plate having a potential difference in between them. Now we have the same thing happening here. Again, this is an induced or created, so we're going to call it EMF instead of voltage. And we can solve for this EMF by using this new equation, where this sigma is our EMF. Again, remember we used it in terms of a battery. B is magnetic field, L is the length of this rod, and V is the speed of the rod. Again, remember from our previous video that the force needed to push the rod at a constant velocity must equal the force of the magnetic field and the electric field created in the process. Again, F must be equal to I, which is the current in amps. L is the length of the rod, and B is magnetic field. So for these examples, it's always going to be important to try to draw a picture. Here we have a rod of 20 centimeters that moves to the right with a speed of 1.5 meters per second in a 3.0 Tesla magnetic field that is pointing out of the page. Again, you can determine the force on the charges and figure out which charges build up on each side of the rod. Now we're asked to determine the induced EMF. Again, that's sigma is equal to B LV. Our magnetic field strength was 3. Our length of the rod was 20 centimeters or 0.2 meters. And then the velocity was how fast it was moving, 1.5 meters per second. Again, in putting all this together, you get 0.9. If we're talking about EMF, then this has units of volts. And again, from our picture, we can use this to determine the area of positive or where we have high potential. Again, this is located at the bottom. This part asks us to determine the electric field, the magnitude of the electric field. Well, if these forces are not accelerating, that means the force of my magnetic field must be equal to the force of the electric field. So, that means QVB must be equal to Q times E. Again, Q's cancel out. We know the strength of the magnetic field, and we know the velocity. So then our strength of our electric field must be equal to 4.5 Newton per Coulomb. So this only gives us the magnitude. The direction is going to be in the positive Y direction, again counteracting the direction of the magnetic field force, and always going from positive to negative. So if you think about this, this is essentially the same result as two charged plates. Again, this function is like a battery. As long as we keep it moving at a constant velocity, it would induce a constant EMF. So if we connect a wire from the positive to the negative, charges are going to begin to flow as current. This is called electromagnetic induction. And this is a pressure or EMF or voltage, which is created or induced, and this creates or induces a current to flow. So let's say that you place two rails made of conducting material side by side in a magnetic field, and then connect them with a wire or circuit. Then place a conducting rod across the rails. Now you can push this rod along the rails with a velocity v. So if the rod is moving, so are the charges in the rod. Again, that means we can use the right-hand rule to determine the direction of the magnetic force on the positive charges, which in this case gives us an upward force, which means that the charges are going to move along the wire in that direction. So if the charges are moving in that direction, that's the direction of our current. When the current reaches the rail, then our current starts to move along the conducting wire, shown here and here. Now, some problems might ask you for the direction of the current in the resistor. In this case, our resistor is over here on this right-hand side, so our current is actually in the negative y direction at that point. So the direction of the current in the entire loop is actually clockwise. And there are three different directions shown here, so make sure that you read the problem carefully. Again, it's always important that you draw your picture. Here we're told that the distance between the rails is 10 centimeters, and the rod moves at 5 meters per second in a 0.2 Tesla magnetic field. And we're asked to determine the induced EMF, which if we know our magnetic field, and we know the length of this rod, which is 0.1 meter or 10 centimeters, and the velocity is 5 meters per second, then we know the induced EMF must be 0.1 volts. And again, to solve for the electric field, again, it's just QE equals QVB, the force of the electric field equal to the force of the magnetic field. Q's cancel, and then my electric field strength is equal to 5 times 0.2, which is just 1. So now we're told that the loop created by the rails and the rod has a resistance of 0.3 ohms, and we're asked to determine the induced current. Well, don't forget your circuit information. So current is equal to EMF or voltage over R, resistance. Again, this is coming from V equals IR, where V is being replaced with EMF. So our current is equal to our EMF that we solved for before over our new resistance, which in this case is just 0.33 amps. Here we're asked to determine the rate that energy is generated. Again, that's another way to say power. So if we now know what our current is and we know what our voltage or EMF is, then our current, which is 0.33, times our EMF, which was 0.1, gives us our power, which is 0.303 watts. And then again, finally, if we're asked to determine the force required to push the rod at a constant velocity through the magnetic field, again, this pushing of the rod induces a current, and the current carrying wires are magnets, then the magnetism of the rod starts attracting the magnetism of the original magnetic field. Again, if you want to move the rod at a constant velocity, you must push with enough force to equal the force of magnetism that is created. So again, the force that you must apply has to be equal to the magnetic force created, which is ILB. Again, we're using ILB because this is a wire or current. We just solved for the induced current. The length between the rod was 0.1 meters, and our magnetic field strength is 0.2 meters. Tesla. So all of this means that you need to push with a force of 0.0066 newtons in order to get this to move at a constant velocity.